today is called torque. And what is torque? Torque is the product of force and the perpendicular distance of a body from the axis of rotation, because torque, you can only talk about torque when a body is set into rotational motion. And rather they do define it, it can also be defined as the turning effect of a force. Let's look at our daily application of torque. While opening a door, while turning of a tap, we apply all these forces we apply, they are referred to as torque. They are forces that are applied in such a way that a body is turned in a rotational manner. So torque is generally denoted by this. And according to the definition, we said it is the product of the force applied and the perpendicular distance r. So where F is what? Force applied, and R is the radius. We call it radius, as the case may be. So then we say torque is equals to F dot R. So we are going to derive more of this formula to make it look more of rotational motion. We can say from our idea in Newton's second law of motion that says F equals ma, force equals mass times the acceleration. This has not really looked more of rotational. So, and at the same time, we know that linear acceleration is equals to angular acceleration multiplied by the radius. So if I substitute this into F equals ma, then I will have F equals m alpha r, where alpha means angular acceleration. Angular acceleration. Now, let's take this back into the formula where we make use of F, 2, and this is 1. So let us put 2 in 1. Then we have torque will be equals to m alpha r dot r, which is actually equals to m alpha r squared. So I can equally write it as m r squared alpha. Don't forget, from our previous video we said mi, which is moment of inertia, is equal to mr squared. I means moment of inertia. So then I can change the formula for torque equals what? I alpha. Meaning that the torque applied on a body in rotational motion is equal to the product of its moment of inertia and its angular acceleration. So this happens to be the formula we are using in calculating our torque. The various questions could come in different ways, of which we might need to also use our steps in deriving the formula. So we actually got this as our third formula. We are also going to look at the relationship between moment of inertia and kinetic energy of a rotating body. The relationship between moment of inertia, torque, and a rotating body, the kinetic energy of a rotating body. Let's recall. Okay, let's write it this way: rotational kinetic energy. Right from our basic knowledge, we know that the kinetic energy of the body is equals to what? 1/2 multiplied by the mass multiplied by the square of its velocity. So this is a general formula known to calculate the kinetic energy of a body whose velocity m, whose velocity v, and mass m. So recall that we have v equals rw, happens to be the value of our linear velocity in rotational form, is equals to what? Radius times angular frequency or angular velocity. So w means angular. Actually, it is represented by omega. So it is called angular frequency. frequency or velocity. So where r still remains the radius and v is what we call the tangential velocity or linear velocity. So on putting that into this formula, v squared is going to be what? R squared over u squared, as the case is. So putting that into this formula, we have Ke equals half multiplied by the mass multiplied by R squared W squared. So on doing this, another relationship has been derived between the kinetic energy and the moment of inertia, where mr squared gives us R W or omega squared. So this actually is the formula for calculating or for determining the kinetic energy of a body in rotational motion, provided we know the angular frequency and its moment of inertia. Please subscribe to our YouTube channel. We are going to bring you more videos. It's free. Just click on the subscribe button and click on the bell beside it. It will notify you when next we drop a new video. Thank you.